Verify the Stokes theorem for the following data: f bar and surface S, which is that is the portion of the paraboloid x square plus y square equal to z, y greater than or equal to 0 and z less than or equal to 1. We need to recall that the Stokes theorem is applicable only to the open surfaces, and let's see this data regarding the surface, or which surface exactly we are supposed to verify the Stokes theorem. This is y greater than or equal to 0, and therefore this is a closed and a bounded surface. Z less than or equal to 1, this is also a closed and bounded surface. Whereas this surface, that is the portion of the paraboloid x square plus y square equal to z, is an open surface, and over this surface only we are supposed to verify the Stokes theorem. Let's see this figure. Now it is x square plus y square equal to z is a full paraboloid which is cut by the plane y equal to 0, and therefore the paraboloid is divided into two sections. It is this part and this part. But of it, which section has to be taken? That is y greater is positive, y greater than 0. So therefore we consider this part of the paraboloid, this section of the paraboloid, such that y is positive. But still it remains to be of infinite dimensions. So let's see this, to make it finite, let's see this condition, that is z less than or equal to 1. Now let's cut that paraboloid by the plane z is equal to 1. This is the surface z is equal to 1, and therefore you get a that is a portion of the paraboloid with finite dimensions. It is this surface. This is the surface x square plus y square equal to z. Now when we start with the verification of the whenever the question is to verify the Stokes theorem, always begin with the line integrals. That is the left hand side of the statement. Here you can see that the line integral along this is entirely a closed path, and it is consisting of two piecewise continuous curves. And when you are evaluating the line integral, always travels in the anti-clockwise direction. So let's see the path C1 first. Whenever you want to identify the path C1, first try to identify it lies in which plane. This curve C1 lies in the plane y equal to 0. It lies in the plane y equal to 0. This part I am talking about, it lies in the plane y equal to 0. But what is the equation of that curve is a question. So substitute this surface is x square plus y square equal to z. Substitute y equal to 0 here, and therefore you get z is equal to x square. And therefore dy has to be equal to 0, because these are the basic requirements in order to evaluate the line integral. Dz is equal to 2x dx. Now this curve C1 is an open curve, and therefore no closed symbol will appear here. Therefore line integral along the path C1 f bar dot derivative of r bar. When we evaluate this f bar dot derivative of r bar, it is a scalar function, and therefore line integral along the path C1, it is y square dx plus z square dy plus x square dx, x square dz, sorry. Now let's see try to use the data for the path C1 to evaluate this line integral. Y equal to 0 is given, so this term will vanish and tend to 0. Dy is also 0, and therefore this will also tend to 0. This term vanishes off. Now we are left only with x square dz. We are evaluating a single integral, therefore the integration has to be respect to only one variable, and we'll see that it is with respect to x. So x square into dz substitution here, so it is twice of x cube dx. Now we need to see what are the limits for x along the path C1. Here x is, your path C1 starts from here, and this is the terminal point. So initial x value is 1 and here x is minus 1. So limits for x run from 1 to minus 1. Now in order to evaluate this function, since the limits are running from 1 to minus 1, we need to check whether this is an odd function or an even function. It's an odd function. We observe that f of minus x is equal to minus f of x, and therefore this is an odd function over this domain, and therefore value comes out to be 0. Now let's see along the path C2 what's the value to the line integral. Path C2. Again, exactly the same way, we need to identify this curve C2 lies in which plane. It lies in the plane z is equal to 1. And now we need to see what is the equation of that curve. Substitute z is equal to 1 in this equation. We get x square plus y square equal to 1, which is a circular arc. So whenever it's a circular arc, we need to represent this curve in the parametric form. Line integral, one dimension, one parameter. Therefore, we have z is equal to 1, x is equal to 1 cos t, and y is equal to 1 sin t. Therefore, dz is equal to 0, dx is equal to minus sin t cos t, minus sin t dt, and dy is equal to cos t dt. Again we see that this is an open curve, therefore you need not write the close symbol there, and therefore the line integral along the path C2 f bar dot derivative of r bar is equal to line integral along the path C2. This dot product, again it is a scalar function, and therefore it is y square dx plus z square dy plus x square dz. Here we now try to use the data for the path C2. Let's see, z is equal to, dz is 0. So this will tend to 0. Let's substitute the values now. Y square. So y is sin t, so it will be sin square, and dx substitution minus sin t makes it minus sin cube t dt, plus z is equal to 1, so z square is 1, dy substitution, so this is plus cos t dt whole of, I'll take dt out common. Now the limits for t, as your path C2 starts from this point till this point, but t limits will be, see this figure, this is y positive, this curve I am sketching in 2 dimension, it is this curve, this is x dash and this is x, this is your origin. You are traversing along the path C2, this is your path C2, and you are traversing from this negative x-axis to positive x-axis in this direction. So your t limits will run from pi to 0. Pi to 0. This is equal to, let's see this function first, the quadrant rule. Using the quadrant rule, value to this function cos t over this domain has to be 0. Whereas this function comes out to be a positive function, and therefore I can write this as twice of. But this minus sign first will use it to revert the limits, and that is 0 to pi sin cube t. And now we'll try to apply the quadrant rule to this part, and this is twice of 0 to pi by 2 sin cube t. Using the reduction formulae, we get the answer as 2 into 2 by 3, that is equal to 4 by 3. So value along the path C2 comes out to be equal to 4 by 3, and the value along the path C1, value of the line integral along the path C1 is equal to 0. But the question, this part along the closed path, line integral along the closed path is equal to line along the closed path. Therefore, along the closed path C, which consists of two piecewise continuous curves, f bar dot derivative of r bar is equal to 0 plus 4 by 3. The sum of the two line integrals, we just add them, and the value comes out to be equal to 4 by 3. Now question is to verify, so we need to work for the surface integral with the same domain, and we'll see in the next video how to evaluate the surface integral over the domain x square plus y square equal to z, y greater than or equal to 0, z less than or equal to 1.